Hello again, everyone. I wanted to make that short video on even and odd functions. It can be kind of an interesting concept, especially since it applies, the words even and odd apply very well to polynomials, but the concept applies to functions way outside of polynomials. So it's something that's good to understand, particularly for those of you who will also take Math 112. So what we're trying to distinguish when we distinguish a function that is even or odd is what kind of symmetry it has. If we look at the graph of a function that, say, looks like that. Now, the nice thing about this function, up to my ability to draw anyway, is that this side looks the same as this side does. Now, the reason that can be handy is as we find, say, local minimums or x-intercepts, or as we learn things about this side of the function, if we know it's an even function, we automatically get the corresponding values on the other side. And that's a really handy thing to know. It can save us a lot of work. It can literally halve the amount of work we have to do. Everything we find out about this side, we automatically know about that side. So it can be really handy. Really, the reason this is called, there's a couple reasons why this is called an even function. You can often think of it as, even numbers can be broken up into two equal pieces. So we're kind of breaking this up into two equal pieces. It's not really why it's called even. I'll talk about that in a minute. But it can be a nice way to think about it. The classic example of an even function is your basic parabola, your y equals x squared. Remember, on your basic parabola, this side looks exactly like that side. It has that kind of symmetry, as if it was reflected about that axis. So this is something that has even symmetry. It's sometimes called y-axis symmetry. Now, we can see a little bit with this example why it's called even symmetry. The reason we get the same answer when we put in a 3 on this side, we get a 9. Sorry, I should make that bigger. The reason we get the same answer on this side as we get on the other side for -3 is because this 2, that even power, is destroying the negative. 3 squared is 9. -3 squared is also 9. So this general quality that if we take our function and evaluate it at a negative value, or at least the opposite of our value, the difference between evaluating at 3 and -3, well, in an even function, there is no difference. F of -3 was the same as f of 3. Whoops. F of -4 is the same as f of +4. F of -1 is the same as f of +1. If x happens to be -8, then f of the negative of -8, so f of 8, would be equal to f of -8. Don't always assume those x's are positive. But if you change the sign, it doesn't change the value of the output, just like x squared. So this is really our definition of an even function. If it has this quality that putting in the opposite of your x value doesn't change your output, then we can call it even, and we know everything we learn on one side is going to be the same on the other side. So, for example, if we want to test and see is y, let me use function notation, is f of x equals 3x squared plus, let's go with 2x minus 4. If you want to know whether that's even or odd, we can check. Now, you might notice it has a even degree, so it might be even. We know this graph is going to be a parabola, so we might think it might be even. But let's check. Again, to check, we want to look at what happens when we put in the opposite of our x value. So I'm just going to put in here negative x and evaluate it. 3 times negative x squared plus 2 times negative x minus 4. And simplify this. And the goal is, can I simplify this and get back to my original f of x? Well, if we look at what this negative does when we square it, when we square that negative, we do end up with 3x squared, just like we had. But here, the 2 times negative x gives us a negative 2x minus 4. So this is our f of negative x kind of simplified down. Now we have to ask, is this exactly like our original function? And clearly it's not. The x squared term worked out, but the linear term, the x to the first, did not. And the constant cooperated. So because we didn't go from f of negative x, didn't return our exact function, it is not equal to f of x. So f of x is not even. Now, you have to be a little careful. A lot of people think that if you're not even, that means you must be odd, because we often kind of have the misconception that numbers are either even or odd. And that certainly isn't the case. If you look at numbers like, 4 is even, 7 is odd, 10 is even, 5 is odd. So it seems like when you think about numbers that they're all either even or odd. But as soon as you do something like 7 halves, that's not an even number, and it's not an odd number. 4.3 is neither even nor odd. Pi isn't even or odd. So being even or odd, certainly you could say all natural numbers are either even or odd. But most numbers are not. Most numbers are just numbers. Being even or odd is actually kind of special. Functions are the same way. Just because you're not even doesn't make you odd. Most functions are not symmetrical. Most functions are not even nor odd. It's kind of special when they are, so it's nice. Now I want to compare that to being an odd function. Again, even and odd is all about symmetry. When we're talking about even and odd, we're talking about trying to use symmetry to be able to take what we learn about parts of the function and apply it to other parts without having to do more work. The other way something can be nice and symmetrical, we can have that same kind of movement on that positive side, but instead of having it reflected exactly on the other side, we can have it turned upside down. Again, up to my ability to draw, those should be the same exact curve. So this is still symmetrical, but the symmetry is a little different. If we evaluate this one at, say, positive 1, we might be getting a value down here like negative 2, assuming my scales are a little different. At negative 1, we're not getting negative 2 again, we're getting positive 2. So it's staying the same, kind of the same absolute value, but if you take your function and evaluate it at the opposite, if you change from positive 1 to negative 1, you sort of get your same output, but instead of being a negative 2, it turned into a positive 2. So if you change the sign of your input, it changes the sign of your output. Essentially flips it upside down. When this happens, it's called an odd function. And again, we'll talk a little bit about why in a second. Sometimes it's called origin symmetry. As you can imagine, if you took that hook right there and rotated it around the origin, this picture would rotate and land back on this picture, as opposed to this one being a reflection, like from your section 3.5, where it's reflected across the y-axis, called y-axis symmetry. This is more rotated around the origin, so it's usually referred to as origin symmetry, or odds symmetry. The nice thing is we test this in exactly the same way. if we wanted to see if f of x equals, let's say, x to the third plus x, we wanted to see if that was even or odd, we can test it the same way we tested to see if it was even. We take it, the function, evaluate at the opposite of x, so negative x if you want to say it that way, and we put a negative x in for every x. Negative x to the third plus negative x. Then again, simplify. So negative x to the third turns into negative x to the third, the odd power. There's that word again, odd. The odd power conserves the negative, plus, well, actually it turns into a minus x when you undo the parentheses. And again, notice this is x to the first. That 1 is again an odd number. Now this is not the original function that we started with, so it certainly isn't an even function. But we can factor out that negative, and that will turn this into an x to the third plus x. And notice this is the opposite of, that's our original function. So f of negative x turned into the opposite of f of x. Generally, when you're trying to see if something is odd, you try to do this. You put in your negative x's, see if you can factor out that negative and get back your original function. Whereas when you're trying to find if something is even, you put in the negative x, simplify, and see if you can just make the original without a negative on it. Now this worked precisely, so this, well, just say, so f of x is odd. It has that odd function quality. Hopefully that's helpful. It gives you a little bit of insight into even and odd. A couple of things to be careful with. We do call, the word odd comes from the fact that if every term is odd, the polynomial is going to be an odd function. Even comes from if every term is of even degree or a constant, you will be even. The fact that this 2x to the first was an odd degree term is why this didn't end up being even. Remember that negative 2x squared is what didn't work. So people often associate, oh, even means your powers are all even. Odd means your powers are all odd. But you got to be a little careful. You have to think of your constant as an even term. So if we'd had, for example, put a plus 2 on this, it wouldn't have worked. We'd have had a plus 2 here, it would have turned into a minus 2, and it wouldn't have matched. Also, this idea of even and odd functions works for things that aren't polynomials. The word even and odd comes from our understanding of polynomials, but there are functions that have no powers at all that are still even or odd because they have these qualities and these symmetries. So be a little careful about generalizing. Odd functions mean odd powers, even functions mean even powers. That's somewhat true for polynomials, but it's not true in general. We really want to know these two definitions. To be odd, the function evaluated at the opposite of x is the opposite of the original value. The function evaluated at the opposite of an input x is equal to the original value for even. Hopefully that helped. Again, if you have any questions, let me know. And if you want to see other videos, let me know.